Ba ba da ba ba da ba 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 da ba ba. Hey you guys, thanks for watching our video. It's mandatory, so I really shouldn't be thanking you, but thanks for watching anyway. So we chose the subject of chapters 3.1 through 3.3 in the book. Just a little advice before we begin. If you want to get the most out of this, we suggest not only listening to our lesson, but reading the chapter if you're confused. You can also ask us questions because we like to pretend we know what's going on with our lives. If we fail you, you can always talk to Professor Zollinger. Infinity has been a lot of fun for us to work on, and we really hope you enjoy this video. Yeah, so enjoy this. Fade out music. Bum ba bum ba bum 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 ba-dum ba-da-da-da-dum ba-dum bum 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 bum.
Alright, wake up. You are about to learn some good knowledge about infinity. So sit up straight, sit your little bahookies in the chair nice and comfortable, and get your notepads out because you're gonna learn and you're gonna like it.
What is infinity to you? To us, infinity is beyond. Infinity is not even a number. What numbers we know now are only a small dent in the number world. There are so many numbers out there.
Alright, we're going to get an idea of how big infinity truly is. So if you look at this really big number that we took a lot of time and effort in typing, I mean, it wasn't random at all. This number even is absolutely nothing but just a tiny, tiny point on a scale in infinity. Here are some more examples of giant numbers that would mean nothing if we were looking at all of infinity as a whole.
Okay, I got it. I got it.
We apologize for that interruption. Branson has been sent to the corner. Anyways, so there's only one apple per one hand, and by this knowledge, you know that each hand has an apple in it. Each apple has a hand around it, so therefore you know that you have the same exact number of apples as you do hands. And then you don't have to count, because counting to 2 is hard. So we're not doing that. We're just same number of apples and same number of hands, and that's all you have to know.
Please consider the following.
Forget everything you think you know.
No, alright, I'm good. I got it.
Alright, just forget everything you've ever known about counting. Forget that numbers mean anything. Do not think in number form in order to fully comprehend this. You do not have 5 fingers on your right hand. Instead, you have the same number of fingers on both your right and left hands. So, we're going to show you a little demonstration about what we mean by this.
Please consider the following.
Branson,
17. What?
did you forget how to count to 5
I
again?
did.
Ah, that's a bummer. Well, do you want to know, are you trying to make sure you have as many fingers on your right hand as you do on your left?
That's my problem.
Oh, I understand that, man. Let me help you out. We're
You
going
can
to
help
use
me?
something called one-on-one correspondence.
Okay,
You don't need
okay.
to count. Okay, now put your thumbs together.
Thumbs? Together.
Okay, so we know we have 2 thumbs.
Okay, okay.
Now put your next closest finger together.
I know the next closest
There
finger.
you go.
Very good.
All right, now next finger.
Next one.
Nope, the other finger. The other finger, Branson.
Okay.
Okay, now this finger,
Yeah, okay.
and next
okay.
the pinky.
Like that.
Now, do you have any fingers left over on either hand?
I do not.
No, that means you have a perfect one-to-one correspondence. You have as many fingers as you should have.
Wow.
Yeah, and this concept can also help us learn more about infinity.
Okay, I'm back. So, let's talk about numbers. Remember that one time I said forget about numbers? We're going to talk about them. I lied. Okay, we have integers. These guys are fun. It could be any negative or positive whole number. That's like 1, 2, 3, 4, 5, or negative 1, 2, 3, 4, 5. Now, there's natural numbers. Those are organic. They're any positive integer is a natural number. So 1 through 3, 4, 5 is they are natural numbers. They cannot be negatives. Get it memorized. Rational numbers are pretty much fractions. So 1 over 2, 10 over 13, 14 over a billion. That's a fun little fraction. Rational numbers. Irrational numbers are any numbers that cannot be displayed in a fraction that are like too stinking complex. So pi is a nice little irrational number. 3.14159265, all that junk. Real numbers are rational and irrational numbers. They can be any of that stuff. So fractions and decimals. So have fun remembering that stuff when you're not supposed to remember anything you know.
Positive integers in infinity. If we take all natural numbers, 1, 2, 3, etc., then we have an infinite amount of integers. But what happens if you take out the 1? Now you simply only have 2, 3, 4, etc. So what has changed? Do you have one less infinity, or does it even matter because you still have an infinity? Or is your brain just broken now? Because mine is.
Nervous wreck.
So do we actually have one less in infinity? This is a logic where you're lining up all the numbers 1, 2, 3, 4, 5, etc., and then 2, 3, 4, 5, etc. But this form of thinking is actually incorrect because you are corresponding the number of values as opposed to the one-to-one correspondence where you're just lining up if there's a number or not. So you can't really do that. Infinity is infinity is infinity. So in this example, we're lining up 1, 2, 3, 4, 5 with 2, 3, 4, 5, 6, but we're lining up one to one number to one number. So by the logic of one-to-one correspondence, there is the same amount of integers in both infinities. Therefore, the natural numbers minus 1 is still equal to the natural numbers as a whole infinity.
Please consider the following.
Okay. With infinity, you need to forget everything you ever know, including counting. So with this, we're going to match each other up and see if we have the right amount of X's and O's. As you can see, we have one O left over and no X's. This is an example of a not one-on-one correspondence. Of not a one-on-one correspondence.
Okay, we're playing ping pong, but not with just one. We're using infinity ping pong balls. Okay, this is gonna be a long game, so start stretching while I'm talking. We have a lot of ping pong balls. I'm just gonna read it. Please consider the following.
Please consider the following.
You have a ping pong ball numbered for each natural number that fall into a barrel. Remember what a natural number is? 1, 2, 3, 4, 5, all that. This lasts exactly 1 minute. How many is that? 60 seconds. And in that minute, an infinite amount of tasks are about to take place. Once 60 seconds have passed, the alarm goes off and we are completely done. So you're gonna be playing ping pong for a while.
This is your first task in the ping pong ball game. 60 seconds are on the clock. At 30 seconds, 10 balls fall into the barrel, numbers 1 through 10. We reach in and remove the ball numbered 1. 9 balls are left in the barrel.
The suit's holding up.
But he's not.
He can do it. I know he can do it.
This is your second task. 30 seconds are left on the clock. At 15 seconds, 10 more balls fall into the barrel. These ones are numbered 11 through 20. Now you have to reach in and grab ball number 2. 18 balls are left in the barrel.
You can do this now. Run, Barry, run!
Alright, this is your third task. We now have 15 seconds left. The task must be performed in 7.5 seconds. 10 more balls fall in, numbers 21 through 30. We now remove the ball numbered 3. 27 are left in the barrel. This pattern continues on infinitely.
It's not true. That's impossible.
Search your feelings. You know it to be true.
So obviously this experiment is impossible because eventually we would be working in time limits of a fraction of a second. In just task number 6, we would have to work in 0.937 of a second. Eventually we'd be working faster than the speeds of light and sound. So here is the big question we have for you.
At the end of 60 seconds, how many balls are left in the barrel? Are there any? And if so, what are the numbers on the balls? Could it be ball number 3? No, because ball 3 was removed during the third stage, when numbers 21 through 30 were put in. How about number 45,671,803? Well, it cannot be that one since it was removed during the 45,671,803 stage of the experiment. So how many are actually left at 60 seconds?
The actual answer is that none are left in the barrel. So because all of the balls were numbered and systematically removed, we can name the exact moment that any one ball was removed. Therefore, at the end of a minute, there are no balls left in the barrel. By this logic, we can convince ourselves that at the end of 60 seconds, there is nothing in the barrel. Did we break your brain yet?
Nervous wreck.
All right, so we're going to explain this a little bit more. Like we were saying, because each ball is numbered, you cannot name a ball that wouldn't have been removed at a certain time. And because this is so impossible, we're trying to combine possible with very impossible. But we're playing with the fact that we work infinitely in 60 seconds, but that time also ends at 60 seconds and that everything is done. So hopefully that makes sense. We thought it was kind of cool. Enjoy contemplating that. Yes.
Please consider the following.
Alright, so when you think of infinity, not all infinities are the same size, which kind of is a weird concept, but it's true and we can prove it. So we have the infinity of natural numbers, which is 1 to forever, but that's only so big, even though it's infinite, it's only so big, because when you compare it to an infinity of all integers, you can see something. So we have a -1 and a 1, a -2, a 2, a -3, a 3, and we'll just do one more. ... Okay, so when you're looking at this, you can see that using one-to-one correspondence, this is so far behind where this already is, which means that this infinity already is going to have twice as many integers in it as the natural number infinity. So this infinity is a lot bigger than this one. And now I'm going to do a different example so you can pause it. Okay, so here's another example of the natural numbers versus the integers. So natural numbers start here, and they go this way forever and never end. But the integers, all integers, they go forever in this direction, as well as forever in this direction. Doodly-doodly-doo. So, it's another example right there.
Papa Cantor. Around the year 1872, George Cantor proved that infinity isn't one set size, but rather that they are multiple sizes of infinities. Daggum! Tried to grasp this concept. Other mathematicians called him nuts and had him thrown into an insane asylum.
Okay. Put this down just a little bit. Okay. George Cantor, like Galileo, was ridiculed for a lot of his ideas. And one of those ideas was that you can have infinity but not have one-on-one correspondence. As Asia already demonstrated, some infinities are bigger than others. And in this case, we're going to show you an example of one way that you can have two infinite sets of numbers, and yet one of these numbers won't use all of its options possible. So natural numbers, of course, are 1, 2, 3, 4, 5, positive integers. Real numbers can be decimals, right? So she has to go 1, I can go 1.1. That's one correspondence. I can go 1.11, another correspondence. 1.111, another correspondence. These are all different numbers, you see. And so I can go on infinitely like this, and I'll never hit the number 2, or anything beyond it even. Whereas Ashlyn will keep on going infinitely higher and higher and higher up. If Ashlyn keeps on going infinitely, she will use every number at her disposal. If I keep on going infinitely, I won't even use a fraction of the numbers at my disposal, because I can go infinitely from 1 to 2 without ever stopping. I can always find new decimals.
The monkey theorem. Alright, to help you understand infinity a little bit better, we will introduce what is called the monkey theorem. It's quite simple. If a monkey were to pound vigorously on a typewriter for an infinite amount of time, he would eventually have the whole works of Shakespeare written. That's bananas!
Infinity is a hard thing to comprehend. Here's one way to think of it. If you were to give a monkey a computer and it started typing randomly and it went on infinitely, that monkey would eventually rewrite the entire works of Shakespeare and every great novel ever written. Hey, Branson! Branson, come here! Come here! Hey, Kraken boy!
Because he's typing on these letters, eventually, like, every written work is going to appear in his random typings, which is insane. But it's what would happen. So that's cool. Monkeys.
An infinite number of mathematicians walk into a bar. The first one orders a beer. The second one, a half a beer. The third, a quarter of a beer. The barman says, "You're all idiots," and pours 2 beers.
Alright, so this is an explanation of that joke. Because there are an infinite number of numbers between 1 and 2, there's 0.1, there's 0.01, there's 0.001, and so on. And when you're dividing numbers in half, there's also an infinite number of those. So 1 to 2 is not just one number, there's an infinite amount of numbers in between. So that's why it's funny, because if you have 2 beers, you can infinitely, I mean theoretically, infinitely pour half of what was before and never run out, because you never get to 2. That's the joke. Funny, huh? Yeah.
Question number 1. How many bedrooms are in your apartment? How many people live in your apartment? Is this an example of a one-to-one correspondence? How could you know without counting?
Question number 2. Explain in your own words, use drawings if it helps, why the 2 beers joke works.
Question number 3. Explain how there are different sizes of infinity. We'll give you a hint. Natural numbers, irrational numbers, real numbers, etc.
To infinity and beyond!